Bun găsit la emisiunea Știință și Cunoaștere. Vă spuneam nu cu mult timp în urmă faptul că pe parcursul anului 2013 am avut ocazia de a realiza mai multe interviuri cu invitați din străinătate. Aș putea spune chiar fără să exagerez că au fost câțiva dintre cei mai renumiți din lume, cercetători, profesori și filozofi cu studii și calități excepționale. Într-un anume fel, fiecare nouă emisiune a devenit ca o carte de vizită, care ulterior mi-a permis să intru în legătură cu personalități de notorietate pe plan internațional. Dar acest lucru s-a întâmplat nu doar prin intermediul internetului, ci și cu ajutorul unor împrejurări foarte interesante, deoarece, de exemplu, în cursul lunii august a sosit la Cluj unul dintre cei mai de seamă matematicieni de la Institutul de Tehnologie din Massachusetts, profesorul Max Tegmark, având preocupări cu totul speciale în ceea ce privește matematica, deoarece, așa după cum veți putea afla peste câteva momente, domnia sa a publicat recent o carte care se numește Universul Matematic. Fiind anunțat de prezența sa la Cluj, am reușit să programăm o sesiune întreagă de 3 ore de discuții chiar la sediul TVR Cluj și țin neapărat să mulțumesc echipei tehnice pentru ajutorul acordat într-o perioadă extrem de aglomerată care a fost luna august. Hello and welcome for the first time in Science and Knowledge on TVR Cluj in Romania.
Mulțumesc foarte mult! Vorbesc puțin romanește, nu foarte bine, so maybe we should continue in English.
Yes, I am happy that you know something about us and about our language. Is it your first visit?
It's actually my third visit. I was here last summer also to visit my wife, whose relatives. I have the good taste of marrying a Transylvanian, Mihaela Kita, and I also was here in 1990.
In 1990, so long ago.
Yeah, it was very interesting to compare Romania during the Mineriad, right after the revolution, with Romania now, and it makes me very happy to see how much better things have become.
Well, very nice to have you here on our studio for a very fascinating talk about cosmology. It is for the first time when we have this subject in our program, Science and Knowledge, because there are so few specialists who knows cosmology and who can explain it for the untrained public. So we are now getting into the subject. In this program we will debate the part 1 from cosmology, which is about a short history of our universe. What are we referring to when we say our universe?
When we talk today as scientists about our universe, what we mean is basically this: the spherical region of space from which light has had time to reach us so far during the approximately 14 billion years since our Big Bang. So, in other words, there is probably more space outside of this, but we can't see it yet because the light from farther away has not had time to come to Earth yet. And this is what we mean by our universe. And our great challenge as scientists is to try to understand what is inside of this universe, to explore, make maps of what's inside of here, and understand better how it began and its ultimate fate. So our planet is right in the middle of this enormous sphere of space, our universe.
And the shape is spherical, or this is only a model?
So what's spherical here is simply the part of space that we can see. So this is a little bit like if you and I went for a walk in Cluj on a day with a lot of fog, then we could not see very far. Maybe we can only see 100 meters in all directions. Then we'll look to us, all we can see is a sphere of radius 100 meters. In each direction, if we look 100 meters away, it just looks like white fog.
Oh, yeah.
And that does not mean that we are in the center of something. It just means that we are in the center of the sphere that we can see. If we walked somewhere else, we would see a different part of the space in Cluj of radius 100 meters. And it's the same with our universe. If there's another galaxy over here, the people who live in this galaxy, they would call this their universe, this part of space. In the case of the fog example, the reason we can't see farther away is just because there's something blocking the light. There's the fog in the air. In the case of our universe, what's blocking our view is not that there's anything in the way. It's just that it takes time for light to go from one place to another. So normally when we turn on the lights in this studio, it feels like it gets light immediately, instantly. But actually, if we measure very carefully, it takes 1 nanosecond, 1 billionth of a second for light to go this far. So if we look at the sun, for example, it's so far away, it took 8 minutes for the sunlight to get here. If the sun were to suddenly stop shining, we wouldn't notice, for 8 minutes. And if somebody were looking at us from a distant solar system, it might have taken 300 years for the light from Earth to get there. They would not see then Cristian Muresanu and Max Tegmark discussing cosmology, but they might see maybe Vlad Tepes fighting against the Ottomans because they're seeing the way Earth was in the past. So what this means is that if you look super far away, there are places in space which exist, which are so far away that the light from there has actually not had time to reach us yet. Because our universe had a beginning. Our universe is only about 14 billion years old. And if there are things that are sufficiently far away, the light has not reached us yet. And what parts of space can we see? This is the part from which the light has had time to get here so far. If you want to know what's here, you have to wait 1 billion years longer until this light also has time to reach Earth. So this is why
how big is the universe? And what are the methods used for measuring the size of our known universe?
So that's a wonderful question, because again and again and again, we humans have been surprised to realize that our universe was still bigger than we thought. Over 2,000 years ago, Eratosthenes in ancient Greece, in Alexandria, figured out the size of the Earth. And people were very impressed. Wow, it's enormous, this planet, much farther than anybody had traveled. And then, of course, later we realized that Earth was not everything. Earth was still just a small part of this much bigger solar system. And it was quite difficult to figure out, actually, the distance from the Earth to the Sun. The ancient Greeks got it wrong and thought that the solar system was about more than 10 times smaller than it actually was. So it was only actually in the last few hundred years that we realized how big our solar system was. And if you look at and yet the stars are much, much farther away than the planets that we see in the sky. So the stars, as we see at night, as I mentioned, might be so far that it's taken hundreds of years for the light to reach us. And we know that actually through a very clever technique. If you try hold your finger up in front of you like this, or maybe your pencil like this.
Yes.
Or take your thumb and then blink with your left eye and your right eye like this.
Oh, yeah.
And you know what? You notice it looks like your finger jumps back and forth.
Yes.
It's
yes.
Left, right. If you put your finger closer to your eyes, and those who are watching this program should try the same thing. Look at your finger and keep blinking with the left eye, the right eye. The closer your finger is to your face, the more it jumps. So you can use this to figure out how far away the finger is. And this is actually how our brain uses the fact that we have two eyes.
And how is this method called?
So when you start talking about the eyes and how the brain figures out how we see, this is called stereoscopic vision. But we can use the same thing in astronomy. It turns out that if you, during the course of a year, if this is Earth, and the Earth is going around the sun, when you take photographs of the sky and the stars in the summer, Earth is in a very different place from in the winter. And what you see is that some stars, if you take a photo in the winter and in the summer, some stars jump back and forth.
Yes, yes.
Just
they
like the
have
finger does.
some oscillations. And
This is called parallax in astronomy, and it's this exact same idea. And the more the stars jump in position between winter and summer, the closer they are. And we can use this to measure exactly how far away they
yes,
are.
yes.
And the result is that some stars are incredibly far away. And so, for example, when my grandmother was a child, and when she went to school, that was what they thought was the entire universe, our solar system, and then a bunch of these stars. Only in 1925 did it become clear that actually our universe is much bigger, that actually we are part of this galaxy, our Milky Way galaxy, with hundreds of billions of stars that form this beautiful pizza-shaped disk with spiral arms, which is so big it takes 100,000 years for the light to go from one side to the other. And that there are also other galaxies that are so far that it takes millions or even billions of years for the light to reach us. And in fact, I've been very lucky in my career to get to spend a lot of time on this project called the Sloan Digital Sky Survey, where we made the biggest map ever of our universe in 3 dimensions. So we mapped out inside of this sphere, where are all these galaxies in 3D, and then you can put all this information in your computer, and you can make a flight simulator program and fly around in our universe and see that we humans in our solar system are all part of something much bigger. And
but we are returning back to this idea in our next parts of the program. How can we learn about what happened billions of years ago?
Yeah, so it's quite interesting that it's easier for us to figure out what happened billions of years ago than to what happened exactly 50 years ago, or what happened during the Romanian Revolution and so on, because as we talked about earlier, the sky is a little bit like a time machine. When you look into the sky, you actually see the past. We see the sun 8 minutes ago, we see stars hundreds of years ago, thousands of years ago, and we can see galaxies the way they were billions of years ago. And what we've discovered, which is very interesting, is that when we look it seems like in all directions in the distant universe, things look fairly similar over there and over there. We see lots of beautiful galaxies. And that means that probably it was also quite similar here billions of years ago to how it was in all those other places. We can see how it was over there billions of years ago far away with a telescope. We can see how it was over there billions of years ago by looking with a telescope. And we can therefore learn a lot about what it was probably also like over here. And what have we learned? Well, the way I think about it is if you imagine that that I'm teaching, I'm giving a lecture, I'm standing up and I'm looking into the classroom. And if we imagine that each of the people sitting in their chairs are galaxies, what you see is very strange. You see very old people in the front row. And then you see slightly younger people, and then you see teenagers, and then you see a row of 10-year-olds and a row of 5-year-olds, and then you see a bunch of babies sitting in the back, and then behind them there is a row with no people. And then at the very end, at the back of the room, the wall is glowing in a strange way. That's sort of what our universe looks like. What does that mean? Well, remember we're looking farther and farther back in time? So the galaxies we see nearby are old. They are as old as our own galaxy. But when we look farther away,
they are much younger as we are looking much further.
Exactly. So we are seeing that when our universe was young, of course, the galaxies then were also young. They hadn't had time to grow old. The galaxies then are smaller. They are not finished in their development. And when you look very far away, you see just tiny baby galaxies that have just been born. And I mentioned the last row has no people in it at all. That's because if you look really far away, there are no galaxies. It's just dark. Because you're looking so far back into the past that you're looking at the time before the galaxies were born. And all there was at that time were the raw materials, the gas from which the galaxies were later formed. So it's fantastic. We can see the history of our universe in front of us like this with a telescope by just looking really, really far away.
But in the same time, the things which we are looking at very, very far away, we are not sure if they still exist at this moment.
That's right, and in some cases they do not exist. We've learned that stars are a little bit like people. They are born, they live, and then they die. And we are lucky that our sun is a very long-lived star. Our sun is about 4.5 billion years old, and it will live for another few billions of years. But some stars are much bigger than our sun, and they shine much brighter, and they die much younger. Sometimes they die in a big explosion. And many of the stars we can see with telescopes are actually not there anymore. Many of those galaxies we can see with the Hubble Space Telescope, if you looked at them, if we could see them today, would look completely different.
What are the most important periods in the history of our universe?
So it's very interesting. Just like in human history, there are certain distinct periods that were quite different. We learn in school about the Roman Empire, about when the Ottomans controlled parts. We're here in Romania and the Revolution and so on. Similarly, in the universe, there are these different periods. If we start today and we go backward, right now we might call this the galaxy period. There are these galaxies with stars and planets and life. The first thing that's really striking when you look a little bit farther away is you see that all of the distant galaxies are moving away from us. And this is what we mean when we say that our universe is expanding. Everything is flying apart. Now, when we look at a picture of space, we see galaxies and we see black in between. But that black is not vacuum, it's not empty. It's actually gas, mostly hydrogen gas. It just looks black because it's transparent. And we all know that if you take gas and you make it expand, it gets colder. That's how a refrigerator works, or an air conditioner. So our universe has been getting colder and colder, which means in the past it must have been hotter. And so when we go farther and farther back in time, we have a universe which is very hot. And if you look at the way our universe was about 13.8 billion years ago, about 400,000 years after the beginning, it was so hot that the gas actually turned into a different form, into a plasma. We learn in school that if you take water, and really cold water, it's solid, it's ice. You warm it up, it turns into liquid. You warm it up again, it turns into gas, steam. If you heat it up, a gas up, it turns into a plasma. And a plasma is not transparent. So the way it looks is, if you look into the universe far away, you see transparent gas, and then eventually you see plasma. So it looks like a wall of plasma that you cannot see through behind all the galaxies.
Yes.
That's what I meant when I said that at the back of the classroom, the wall, there's a glowing wall. And that is what we see pictures of here at the edge of our universe.
But this is a thermographic map, a temperature.
That's right. That's exactly right. Because this
so
plasma...
the hottest are the red.
Yes.
And the bluish are colder regions.
Exactly. And so this plasma was very hot. It was about 3,000 degrees, about half as hot as the sun is on this outside. And in all directions, if we look really far away, we see this wall of plasma. So it looks like we are surrounded by a wall of plasma. And fortunately, this radiation from the hot plasma cooled off when the universe expanded. So when it comes to Earth, actually it's very cold. It's only 3 degrees above absolute zero. It's microwaves. You need a microwave camera to take these pictures. And these pictures were taken by the Wilkinson satellite from space with a microwave camera.
Oh, I heard about 3 different satellites which took some pictures. Kobe,
Yes.
the Wilkinson map, and Planck.
That's right. So for the
Yes.
first to discover that there was this radiation, the first satellite to make maps of this radiation was the Kobe satellite.
The Kobe, but it was not such a good resolution.
No, those pictures were very fuzzy.
Yes.
But it was a revolution in cosmology, the discovery, when it was made in 1992, and George Smoot and John Mather got the Nobel Prize, actually, for this wonderful project, which I think they deserved. But then this American satellite took these better pictures, and then there's a European satellite, which has made even better pictures, which I'm very excited about. I actually worked a lot on, back in 1995, on when we were writing the grant proposal to get funding from the European Space Agency for this. And I'm very happy that this past March, this satellite released these beautiful maps, which are the best maps we have so far. And you can think of these pictures as baby pictures of our universe. You can look at baby pictures of me, when I was tiny. This is what our universe looked like as a baby. It was just this plasma. And you also asked a very good question, why does it look hotter in some places than others? Well, basically, there are two things which have changed about our universe since this early time. One is that the universe has expanded, which has made it transform from being very hot to being cold, from being very dense to being more rarefied. But the other is it's changed from being very simple and boring to being very complex and interesting. Because back then, there were no galaxies. There was just gas, much like the air in this room. But over time, the gas clustered and clumped into more interesting things like galaxies, stars, and planets, and people. And for that to be possible, there must have been some tiny differences from place to place already in the beginning. And that's what you can see pictures of here. It's, when we talk, can you hear me now?
Yes.
That's because of sound waves. So if you take a microphone and you measure the pressure of the air right here, sometimes it's a little bit higher, sometimes it's a bit lower because I
Yes.
speak. It's about 1,000% higher in some places than others, which coincidentally is exactly how the gas in our early universe was. 1,000% more gas in some places and less in others. And then gravity transformed this gas with some sound waves into everything interesting we see. Because if the gas were completely uniform, then it would stay completely uniform forever. But if you have a little bit more gas here, then the gravity from this will pull more gas into this. The gas will fall down towards here, and then you have a bigger clump with more gravity, which can take more gas and more gas. It's unstable, and eventually you make stars and galaxies.
Precisely how old is our universe?
So this is very interesting because we used to argue about whether our universe was 10 billion years old or 20 billion years old when I was a graduate student. Now we argue about...
When I was very young, I heard 20 billion years old.
Yeah, but that's right. But then some people said, no, it's only 10 billion years old, and they could never agree. So cosmology got a bad reputation for being very inexact. People could not make good measurements. Now, after the Planck satellite, we argue about whether it's 13.7 billion years old or 13.8 billion years old. So, and it's probably 13.8 now. So we're getting great precision. So how do we do this? Well, the basic idea is actually quite simple. If there has been a bank robbery in Cluj, and the police on the highway, they stop a car with the robbers in a car full of money, and the car is 100 kilometers away from the bank, and the car was going 100 kilometers an hour, they can figure out when the bank robbery happened. It must have happened 1 hour ago. You just take the distance and you divide it by the speed of the car. And we can do the same with our universe. If we see a galaxy that's very far away, we can measure its distance, and we can measure how fast it's going away. So we can figure out how long ago was the galaxy here, just like we can figure out how long ago were the bank robbers at the bank.
Yes, but there are something very interesting. The car can go away from the bank, depending on what the burglars see the danger. as constant speed, or it can accelerate, not to being caught.
Exactly, and I'm very happy that you asked this, because this is exactly a complication that we have. If you ignore that possible complication, then you only get an approximate answer. You say, well, it's approximately maybe 13 billion years, 14, 15.
It is expanding, but how it is expanding?
Exactly. But to get an exact answer, you really have to know, are they accelerating or are they decelerating? And as a matter of fact, we've been able to measure that now. And it turns out, interestingly, we'll come back and talk about this later, our universe started out by for the first half of the age of our universe, the universe mostly decelerated. That's what we expect, because if I take this pencil and I throw it up into the air, eventually it will stop going up. Gravity decelerates.
Yes.
So the galaxies flying apart will be decelerated. But strangely, during the second 7 billion years, our universe has been accelerating again. And we'll come back and talk about why. But when we put this into our calculations, it turns out that the acceleration and the deceleration almost cancel each other out, and we get back almost exactly the same answer as if we just do the simple calculation that we talked about first. And we get 13.8 billion years. That 13.8 billion years ago, almost everything was in the same place, and our universe was super hot and super dense.
Let's go now towards the very beginnings, and please tell us what is the most plausible theory of how the universe started.
So I should tell you first that we don't know, is the honest answer. There has always in the history of humanity been a frontier of our knowledge. We always knew what happened yesterday, but there was always a time in the past before which we didn't know. And gradually we have been able to push this frontier of our knowledge back in time. As I said, we can see what happened all the way back to 400,000 years after the beginning. And so we understand that very well. We actually have also been able to push the frontier back to the first second after the beginning. Just like we know that there are dinosaurs, because even though we can't see them, because we found fossils, we found bones of a Tyrannosaurus rex in the ground and so on, we have also found fossil evidence of what happened earlier during the epochs we cannot see. So we know that our universe was hotter and hotter in the past. If you take hydrogen gas, and you keep making it more and more hot, then eventually it will become as hot as the center of the sun, many, many millions of degrees. And we know from physics what happens when you make hydrogen this hot. The same thing is happening inside of the sun right now. You get nuclear reactions, fusion reactions, where hydrogen turns into helium and produces lots of heat. So you predict that our entire universe, when it was about 1 second old, was a giant fusion reactor which took the hydrogen and made helium. And but the fusion reactor turned off because the universe expanded and got too cold. And when you calculate how much helium did it have time to make, the answer you get is about 1/4, about 25%. But we can look with our telescopes and we can measure how many percent of the universe is helium out there and far away, and we get 25%. It's very, very impressive. And we can also calculate how much lithium and deuterium and helium-3 we get, and it agrees very, very well with what you predict from this cosmic fusion reactor. So we're actually quite confident that we understand what happened after the first 1 second or so. Before that, it becomes much more speculative, and we honestly don't know, but there are a lot of interesting theories. And the most popular theory in the cosmology community for what happened before that is called inflation.
Oh yes. This one I heard about. Yes, the inflation theory, but it began somewhere in 1980s. Alan Guth formulated.
Yeah, my MIT colleague Alan Guth.
Your colleague with Alan Guth?
Yes, he's in my department. He's a very nice guy. Very nice guy.
And how did you cooperate with him? And
we're good friends. He was over for dinner at our house a few weeks ago. He's a very nice man, and we've also written papers together on other things more recently. But
so you work together with him, yes?
Yeah, and we have students together. I feel very lucky to get to work at MIT together with such wonderful people. So Alan Guth had this very radical idea where you have to make one very strange assumption. You have to assume that there is a kind of stuff which does not dilute when you expand it. And what I mean by that is if you take, for example, if you take ordinary stuff like air and you expand it to twice the volume, the density gets lower because the total number of atoms is the same. The total number of kilograms must stay the same. But he said, suppose there is another kind of matter which will not dilute much. So I put it in I take 1 kilo, I expand it, now I have 2 kilos because the density stays the same. That sounds very strange, but if you assume that, then you can calculate using Einstein's equations that, in fact, what it will keep doing is it will keep doubling its size, doubling and doubling and doubling and doubling and doubling. And if you keep doubling a number over and over, very quickly you get something enormous. You get 1, 2, 4, 8, 16, 32, and soon it gets very big. And in fact, this stuff in the inflation theory, it kept doubling its size extremely fast. So after a tiny, tiny fraction of a second, it had already created something which had more mass than our entire universe in it, and it was flying apart very, very fast. So what's interesting about this is if you start with a tiny amount of this stuff, much smaller than a single atom, it can explain what put the bang into our Big Bang, why there was this explosion, and why you got all this stuff. And after he developed this theory, and other people like Andre Linde and many other scientists elaborated on this, it became clear that this theory actually explained a lot of mysteries that we didn't understand, properties of our universe. And it also gave a beautiful explanation for why there are actually these patterns, why it's a little bit hotter in some places in the early universe than others. And the Planck satellite that just gave us these new measurements has beautifully confirmed this inflation theory. So even if it sounds like a very surprising assumption that there is a strange kind of substance, that it's predicted all of these different things which agree very well with what we measure, and it seems to really work. And that's why people take it so seriously. And there are more things that it's predicted that we're also hoping to test soon. So this is the best theory we have so far for what happened very, very early on.
Yes, but you know, this is such a fascinating subject. We are fascinated by everything which is unknown. So my next question would be, do we know what happened before our Big Bang?
So,
or rather, if we can speculate something about.
So the answer to your first question, do we know, is no. But can we speculate? Da, absolutely. There are many different speculations about what happened before our Big Bang, and even some of the speculations are even more radical, saying maybe it doesn't make sense to talk about before. For example, if you ask, what is there north of the North Pole? What would you say? It doesn't really make sense.
Yes, yes.
And Einstein actually taught us that the whole idea of time that we think we understand so well is actually is much more subtle than we thought. And it might very well be that our Big Bang was the beginning, not just the beginning of our space and all this stuff. Maybe it was in some way the beginning of time also. Or maybe all there was some strange quantum fuzz. We will talk more about this in the next program, about quantum mechanics.
Yes, yes.
Where it somehow didn't really make sense to talk about space or time. And then gradually, time and space sort of emerged. There are many different speculations. I feel that right now, the frontier of our knowledge is basically to try to test inflation. And if we can make a lot of progress on that, we'll be in a better position to try to take the next step.
And among the speculation, is there anything about the possibility that maybe time and space to be much older than the universe?
One category of speculations is that there was something before our Big Bang, that maybe there was our universe collapsed and somehow bounced back again. There are a lot of problems with that, so most people don't believe that that works, that you would just make a giant black hole instead and nothing could come out. But there are some people who are pursuing that, and I think actually it's really fascinating that, as you said, we humans, you know, it's hard for us to understand things much bigger than us. It's really remarkable that we've been able to understand as much as we have, because, and this is something that I think we should be very grateful for. We are much smaller than the stars.
Yes.
But somehow the properties we have to be able to think critically and be creative and use our imagination has enabled us to really figure out remarkable
within
things.
the scale of the smallest, tiniest possible particle and the largest cosmic object, we are in the middle. Someone took a
Yes.
map, you know. And,
That's right. That's right. And not only that, but we're also the most, your brain is also, our brains are the most complicated objects that we know of in our entire universe. We are much smaller than the sun, but much more complicated and complex, and I think in that way much more interesting. And we are able to think because we're much bigger than the atoms and because we're much smaller than what we're part of.
Yes, and also there is a theory that space and time would not be only some concept, some abstract concept, but space, for example, would have a geometry which is creating, expanding from a tetrahedron shape, which is the smallest possible three-dimension space which we can create. It's a tetrahedron. We cannot create something which is less point, but the largest one is the sphere, which has an infinite number of points.
Yeah, there are many interesting theories like this.
Buckminster Fuller, for example.
Yes, exactly. And there are many interesting theories like this, and I think it's important that we are humble and modest, and that we never dismiss theories and say, that must be wrong because because it seems counterintuitive or strange. Our job as scientists is not to tell our universe how to behave, to conform with our preconceptions, but to be modest and to look at our universe very carefully and see how it actually is. And maybe it is indeed in some way which is very different from how we thought.
So we should be open to all possibilities, because it will never know maybe in the future which one will be more accurate than the other.
Absolutely. I'm glad you mentioned this, because to me that is the single most important idea in science. We should be open to all possibilities. We should always question, we should always ask questions, we should always question authority. Everything we believe in now, it might still be wrong. Sometimes even Newton's theory of gravity, for example, which was very successful, it was not quite correct, and Einstein came up with a better theory, and so we should always be open for new possibilities. If we're not open to new possibilities, then we will miss the opportunity to make wonderful discoveries and also to discover new technologies.
Yes. I also read a lot about a theory which, due to the copyright problems, I am not allowed to present to our viewers, and I made an interview with that physicist, but later on his manager forbidden me to present it. And I am happy you are now here, and you can either confirm or deny, or we can talk freely about all the theories of the universe. What is happening with the universe now? Is the universe expanding, contracting, or dissipating, accelerating or decelerating?
Yeah, so right now, we know for sure that our universe is expanding. So again, what we mean by that is if you take any two galaxies far away from each other, they are going still farther apart. But the second question is, how is that expansion changing? Is it expanding faster, accelerating, or is it decelerating? And as we discussed, the natural guess would be that things should decelerate because gravity always tries to slow down something which is going up. But interestingly, we've measured now very carefully with two different methods that our universe is now accelerating. And this is so shocking that it was hailed as the breakthrough of the year about 13 years ago, and it was given the Nobel Prize in physics, this discovery. And the reason that it is accelerating is that there is something which is creating an anti-gravitational force. So again, normal gravity, if you throw something up, will make the thing gradually move up slower and slower until it stops. So if something is falling upward faster and faster, there must be something which is instead pushing instead of pulling.
Yes.
And that's something, we don't know what it is, but we've made up a name for it. We call it dark energy. And incredibly, it makes up about it makes up about 70% of all the stuff in our universe. Most of the stuff out there is actually not atoms, the kind of material that you and I are made of, and not even dark matter either, which we can talk more about. But it's this strange dark energy. And we don't know what it is, but we really want to know what it is, because this dark energy is what's going to determine ultimately the future of our universe. And another interesting thing about dark energy is it's made people believe more seriously in inflation that we just talked about. Because before you could say, well, yeah, it's a nice theory, it predicts nice things, but surely there cannot be a substance which has this property that it won't dilute, that you take 1 kilogram and it expands into 2 kilograms. That's ridiculous. But dark energy is exactly like that. And we know dark energy exists. That's what the Nobel Prize was for. So if this kind of stuff can exist now, it's actually not so crazy to think that it could have existed also in our early universe and caused the inflation.
But is that somehow part of someone calculated the density of the vacuum and obtain such a huge density that it is almost unbelievable? The entire mass of the normal matter of the universe is, if we could contract it, it will be comprised into a centimeter cube of...
Yeah, so it's very mysterious what this stuff is, and if you make the simplest calculation you can as to what should the density of dark energy be, or the density of I should say that dark energy is not like water or salt or some ordinary substance that you can have, because I have water here, but there's no water there. You can have a clump of ordinary matter, but dark energy is not like that. Dark energy has the same density everywhere in space. It's completely uniform. So it's as if it's a property of space itself, that the empty vacuum has a density. And when you make the simplest possible calculations of how dense the vacuum should be, you get crazy big numbers.
Yeah.
So for a long time people said, those calculations have to be wrong. The true answer is probably 0. But now we've measured it, and the answer is not 0. In fact, 3/4, or 70% of the stuff is dark energy. In the next program, when we talk about parallel universes, I'll tell you more about an explanation on how
Yes.
how that might work.
Yes,
But we should also mention, I think, dark matter, because I said we humans have to be humble, and we have become a little bit more humble when we realize that not only is our universe much bigger than Earth, but we are not even made of the majority substance. We are made of atoms. Everything we see is made out of the same kind of particles. But we are only 5%. 70% is dark energy, so that means 25% are still missing. What's that, 25%? That's what we call dark matter. And if you look into space, sometimes you can see things, you can figure out that something is there.
Let me a little refresh. From 100%, 70% is dark energy.
Yes.
20% is dark matter and 5% is the normal matter we see?
Yeah, let's say about 25% dark matter and about 5% is normal matter. Yeah, all the atoms, gold, hydrogen, oxygen, iron, all that stuff, only 5%.
5%.
So there's 5 times more, 25% of this dark matter. What is that? And why do we believe that it exists? Well, if you look at for example, the sun, and you see that Earth is going around the sun, you can figure out how heavy the sun is, because we know that the reason Earth is not going in a straight line but in a circle is because the sun is pulling on Earth. So that gives us a way of figuring out how many kilograms are in the sun. And similarly, you can figure out how many kilograms are in the Milky Way galaxy. Vera Rubin in the 1960s, she decided to weigh our galaxy by looking at stars that were orbiting around our Milky Way. She looked at how fast they were going and at what radius. And she realized that actually the Milky Way weighs much more than the stars in the Milky Way. So there's more stuff in our galaxy which we actually cannot see. It's not stars, it's not gas. What is it? And now we've convinced ourselves that this other stuff is not made of atoms at all. We call it dark matter. And we don't know what that is either. It's another big mystery.
Yes,
but most people think that the dark matter is maybe some kind of new particle that we haven't been able to detect yet in our laboratories. There are particles that are very shy. For example, there's a kind of particle called the neutrino, which we have detected now. They're so shy that if a neutrino comes and it hits my hand, it goes right through and out on the other side. Then it hits the ground and it goes through Earth and comes out maybe in China and continues into space. And once in a while, if you build a really big detector and you're very patient, sometimes you can catch a neutrino. And the neutrino's also got a Nobel Prize now for being discovered. So we think that the dark matter is probably some other kind of particle like that that's just very shy. It doesn't like to interact so much with atoms, but once in a while it does. And there are many experiments now around the world trying to catch dark matter particles. And another very exciting development is in Geneva at CERN, at the Large Hadron Collider. Many scientists, including many great Romanian scientists, are working on the Large Hadron Collider.
Oh, yes.
This machine which collides particles near the speed of light and smashes them together to see what comes out.
And the institute is right here nearby the studio. They have a contract with CERN in Geneva, and I interviewed the specialist over there. It's very
Wonderful.
nice.
And I saw them when I came in here also. And what they're doing is it's possible. It might be possible at CERN to actually produce dark matter, because it might be that in some of these collisions, dark matter particles might come flying out, and that would also be a sensation, because then we would, which would certainly give the Nobel Prize, if we discover the particle that makes, or particles that make up the missing 25%. So this is one of the biggest challenges right now in physics, to try to figure out what is the dark matter. Some people try to catch it, some people try to produce it.
But regarding this expanding the universe, if it is accelerating, there are more possibilities. It will be dissipating, or it will continue to create more and more galaxies and stars.
Yeah, that's right. So all we know is, first of all, we know that right now our universe is accelerating. But what about our future? We all want to know about our future, what's going to happen. And there are several different possibilities. And what will ultimately happen really depends on the dark energy. Because right now, 75% of the stuff is dark energy, and the dark energy is not diluting, but all the other stuff is diluting. So eventually there will be 80% dark energy, and 90% dark energy, 99% dark energy. So what the dark energy does will determine our fate. So what are the possibilities? One possibility is what we call the big chill, that our universe just keeps expanding forever, getting bigger and bigger and colder and colder. Another possibility is that somehow the dark energy starts to dilute and eventually goes negative and starts causing deceleration, and that our expansion could stop and our universe would come crashing back together again in what we call the big crunch, basically making a giant black hole out of everything. And a third possibility is that the dark energy instead goes really crazy and starts accelerating things faster and faster and faster, creating what we call the big rip, when the expansion becomes so fast that just everything gets torn apart a finite time into the future. And then yet another possibility, you see, cosmologists have a lot of imagination for coming up with bad things that can happen, is that that you could have what we could death bubbles.
Yes.
That maybe somehow space itself is unstable somehow. Like if you, for example, if you take water and you leave it in a bottle of water, you leave it in your car in Cluj in the winter when it's freezing, if you don't touch the water, it can become super cooled. It can stay liquid even though it's below zero. But then when you touch it, all of a sudden, poof, it all freezes all at once. Some people think maybe our space is like that our space could somehow freeze into a different kind of space.
So it can have weird properties just like water,
maybe.
Which some scientists also discovered that if the water is cooled suddenly at minus 80, 100 below zero, it creates something totally different.
And if this were to happen, if this is possible and were to happen in our space, then you would get like a bubble of destruction.
Yes,
because the space would start changing.
We have time only for one question in this
I should just
program.
say people shouldn't worry so much about this. I don't want to scare our viewers too much. The most likely scenario is probably that our universe is just going to keep expanding for a very, very long time.
Yes.
So we should worry more about the stupid things we humans sometimes do to our planet.
The final question for this part. What does studying the universe tell us about life and our significance in this vast space and time?
That's a wonderful question, and I have to confess to you that I have changed my mind about this, because the more I learned about our universe, the more I learned about how big our universe was, the smaller I felt and the more insignificant I felt. But then something happened which completely changed my perspective. We live in a universe which is very, very large. So far, we have never found life on any other planets, and this is also a very exciting topic. You can make it. You probably have other programs about, but it's actually it is a possibility that we are alone in our universe. That there is no. It might be possible that there is no other life in here, anywhere in our universe, as advanced as us, able to build telescopes, for example. So let's imagine, just for a moment, if that is true, what does that mean about how we should feel? It means that we should feel very significant. If we look at the galaxies with our telescopes and we say, wow, this spiral galaxy is so beautiful. Why is it beautiful? Because we see the galaxy. In this sense, it's not that our universe is giving meaning to us, but we are giving meaning to our universe.
And if we would not be alone?
If we would not be alone, well, then there are very embarrassing questions we have to answer, like why haven't we seen any any life yet, and why haven't they already colonized us? We know that there are planets in our galaxy which are billions of years older than Earth, and we also know that it's, according to physics, not that it's certainly possible for life to travel between planets and colonize. So we don't know whether we're alone or not, but I think it is possible that we are alone, which means that in a way the fact that here on this planet, atoms, we have become aware of ourselves and gotten consciousness and built telescopes and started to appreciate the beauty of our universe. In this case, that's maybe the most significant thing which has ever happened in the entire history of our universe. So we might be small, but very significant. And if you look to the future, right, then space travel is certainly possible. And if we humans don't mess up, it's quite possible that in the distant future, life will spread from this planet and our whole universe will one day be teeming with life, right? And it would all have started then on Earth. I think we have to be very careful with humans because I think this time that we live in is very unstable. I think we cannot just keep messing around with nuclear weapons and all the other technology we have like this for hundreds of years without either something very bad happening, which might even end life here, or us really getting our act together and creating a more stable and harmonious society. And when will this all be decided? Maybe in our lifetime. So I think that not only should we not feel insignificant, but what we and what our viewers here and what the young children in Romania who can go out and study science and so on and change and affect the world, what they do in their lifetime is probably the most significant thing to ever happen anywhere in space and any time in the history of our universe.
Thank you very much, and I hope to meet you again next time for part 2.
Ne vom vrenteni data viitoare la parte 2.
Okay, great. Aceasta a fost prima parte a discuției noastre despre cosmologie și vă încurajez în mod deosebit și cu insistență să vizionați partea a doua data viitoare la aceeași oră, deoarece vom vorbi despre lumi paralele, mai degrabă universuri paralele, și este pentru prima dată când abordăm un astfel de subiect care poate până nu de mult la noi în sală era considerat fie de sorginte ezoterică, fie pseudoștiință. Noi vom face o abordare științifică, cu toate criteriile respectate, așa după cum sper că vi le reamintiți la discuțiile noastre cu domnul profesor Daniel David. Înainte de a încheia, doresc să vă anunț faptul că domnul profesor Max Tegmark vă stă la dispoziție pe pagina sa de Facebook cu orice întrebări legate de cosmologie și chestiuni discutate în cadrul emisiunii. Fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere.